Today we're going to talk about pool ball geometry, or it's also applicable to like mini golf, and the idea of trying to get a hole-in-one on each shot. So just to start by thinking about the idea that we're going to encounter here, we've got a pool table set up. The arrow shows the direction we're going to hit this ball, and with all these problems, we're going to assume that we're hitting it like straight on. So I know that when you actually play pool, you can hit the ball in different locations, and that'll put a spin on the ball, and that changes things. We're just going to hit this straight on, and what would happen to it? So the question is, if we hit it in the direction indicated here with the arrow, is it going to go into a pocket, and if so, which one? So go ahead and think about that. You might want to try to sketch something out. You can discuss it with the people around you and try to decide, are we going to make the shot, or are we going to miss the shot? And if we're going to make it, where are we going to make it? Okay, so if we use the arrow indicated, then the trajectory of this ball is going to be about here. And then the question is, what's it going to do when it hits the wall? Okay, and that's what this lesson is all about. It's going to bounce in some way, but exactly where is it going to take off in a new direction? And underneath this, we have a little arrow there that gives us our hint for how this is going to work, and that's our law of reflection. What the law of reflection says is that angle in is equal to angle out. So what that means is the angle that the trajectory makes with the wall going in should be the same angle that it makes when it heads out in a new direction. So to actually get this, I need a protractor, but I'm just going to kind of eyeball and estimate. It's going to be close. I'm not quite sure. Made that mark out a little bit so it looks optical illusion there. But those two are about the same. It might make it. It might just slightly hit the corner edge, and then it would start doing some bouncing. It's going to be pretty close. It's going to be pretty close for sure. Is it actually going to make? Is it not? We would need a protractor to kind of measure that out and guarantee. But the key to this this activity, as we move through our problems, is this law of reflection, that our angle in needs to equal the angle out. So many of you have if you've played pool, you may have noticed these markings that are around the table, and maybe you just thought it was like a decoration thing they put there. Those are actually there for the purpose of using in these types of problems to be able to guarantee a pocket. So people who are actually very good at billiards use those markings around the table in a way of measurement to determine where the reflections are going to hit. We're going to watch a Donald Duck video in a week or so that actually shows kind of how that works. Donald Duck. I kid you not.
Trick shot competition, like one shot. You two tries.
So we're going to look at a little proof here. It's been a long time since we've talked proofs, but we're going to look at a proof for why this works and also an example of how we would solve a problem with this. So off to the side here, we have a mini golf setup, and we want to try to solve the problem with this. So the first thing I would do is you're going to need some kind of a straight edge for this. A ruler would work great. Otherwise, just an index card or anything that you can use to draw a straight line is going to work for you. But what we want to do is start making a plan. So the first thing I always try is like, can I just hit it into the hole? That would be like ideal. But you know, if I try that here, I'm gonna clip the corner. So that's not gonna work. I can't aim straight for the hole here. So then I'm gonna need to kind of sketch out what might be my best shot then. I think I'm gonna wanna hit somewhere down here so that it's gonna bounce up there. That kind of seems like my ideal shot. Now the question is, where do I aim for along that wall so that it guarantees to work according to this rule of angle in needs to equal angle out? So the way we're going to construct this so that it works is with reflection. Okay? It's our law of reflection, so we're going to use reflection. That's why this is included in this unit. Reflection is one of our types of transformations. When we do these problems, we want to work from the end to the beginning. We kind of want to work them backwards. So what we want to do is take the hole and reflect it across the wall that we want to hit. Okay? So when I did my little sketch, I said we're going to aim for that bottom wall, and we're going to bounce off that wall. So what I want to do is reflect the hole across that wall. Now when you do a reflection, the distance should maintain the same. So what you're going to want to do is take a ruler and line up that hole with the bottom wall, the one we want to reflect over, as close to a right angle as you can make. Okay, you want to line it up perpendicularly with your reflection wall, and we want to reflect it over there. So however far away it is, it needs to go that same distance away on the other side. Okay, so let me grab a little ruler for myself here, and however far away I am on the one side, I want to go equal distance out on the other side. And I'm going to call that point H prime. It means it's the reflection of H. Okay? So I'm taking the hole and I'm reflecting it across the wall that I want to bounce it off of. Now to figure the path of our ball, what we're going to do is instead of aiming for the hole, because we can't, because we're going to end up clipping that corner, we're going to aim for the reflection of the hole. So I'm going to aim the ball towards the reflection of the hole. But I can't make it all the way there because it's going to hit the wall, right? So right about here, it's going to hit the wall, and it's going to need to take a bounce. And that bounce will take it right to the hole. I kind of missed that. Let's try that again. Now the question is, why? Okay, so I'm telling you that it's going to do that. Why? Why is it going to do that according to geometry? So to solve this problem of why, what we're going to do is connect down here to make a triangle. Two triangles really. And they're very special triangles. Because when we did that, I said you want to make sure you line up your ruler perpendicularly with your reflection wall. So we made some right angles there. And I said you want to make sure that when we do our reflection, we're maintaining the distance. So we're the same distance away on each side of that wall. I'm going to label some angles into this problem. Angle 1, angle 2, angle 3. What we're trying to prove here is that angle 1 is equal to angle 2. That our angle in should be equal to our angle out. That's what I told you should happen, but does it really, and how do we know for sure it's going to happen every time? So what's a set of angles in this picture that you can tell me for a fact and give me a reason will have to be the same?
1 and 3.
1 and 3, for sure, are going to have to be the same. What's our reason on that?
Vertical angles.
Vertical angles. If you remember stuff from the beginning of the school year, that's like chapter 2. Way to go, guys. So vertical angles are congruent. We learned that a long time ago. 1 and 3 are a set of vertical angles here. Now we're trying to prove 1 and 2 are congruent. So if we could say like 2 and 3 are, then everything is, and that would be pretty great. Turns out 2 and 3 are. It's a little bit more of a process in thinking of how those are going to be congruent. So we drew in those two triangles there, and those two triangles have a lot of stuff that matches. They both have a right angle. They both have one equal side that's marked, and they actually share another side. So we end up with two triangles that have like a side angle side, or since it's a right triangle, we can call it a leg leg. But those two triangles match, and then we learn this cool little phrase, CPCTC, that if two triangles match, all their pieces should match up together. So 2 and 3 must be the same because those two triangles match up together. So if 1 is equal to 3 and 2 is equal to 3, then 1 should be equal to 2. And what was our reason on that?
Let's start with the D. Start with the D's.
Substitution.
Substitution or
Transitivity.
transitivity. We use transitivity in almost every proof we wrote for a long time. It's kind of a go-to when you don't know what else to do, just do a transitivity. It's been a long time since we've done proofs. We stopped on those. We quitted those. That's horrible. We quit doing proofs at our exam. So we haven't done any in the second semester. So it's been a long time. So it's kind of the basic idea there of not just believing me when I tell you angle in should equal angle out, but kind of seeing that this is guaranteed to happen every time because of the geometry of the picture. So we've got one more problem we want to look at. So when I start thinking of this problem, I want to consider my path. we gotta have a game plan going in here, otherwise it's gonna be bouncing off the walls forever, which is really fun when you're actually playing mini golf. You can just hit it hard and see how many times you can bounce. But, you know, how many holes in one are you gonna get that way? Probably not a lot. So to try to actually do a good job at this, we want to make a game plan. So my first thing I always try is like, can I just line it up? Yeah, no, definitely gonna hit some walls there. So that's not gonna work for me. So then, a couple different ideas I could do. I could maybe aim for somewhere out here and then do that, but when I look at this, like angle in and angle out are far from looking like they're the same. So this is probably, this for sure is not gonna work. That game plan might be able to be altered a little bit. Go ahead. I think I'm going to have to come down here. And if angle in is going to equal angle out, it's not going to make it all the way to the hole. I think I'm going to have to take a couple of bounces on this one. Okay? So I think that is kind of my game plan here. Now we're going to work these problems backwards. So we're going to begin with the final bounce we want it to take. So the final bounce we want it to take is over that wall EF. So what we're going to do, and I'm just going to leave kind of my game plan up here so we can see the process. I want to take the hole and I want to reflect it over its final bounce over the wall EF. So line it up as close to a right angle as you can make it with your ruler. And we want to go the same distance out on the other side. And here I'm going to call that H prime. That's my reflection. Now working backwards, we have another bounce to take. So what we want to do is now bounce off of the next wall, working our way backwards. Now to do this, we need to actually extend out this bottom side because I want to reflect not the actual hole, but I want to reflect my reflection. Okay? So I'm going to take that H prime point and flip it over the bottom wall now. Unfortunately, the margins of the paper just did not work in my favor here, and it's going to fall right off the bottom of your page. Right about here for me, since I can go off the bottom of my page, but it's going to land right off the bottom of your page. But we want to reflect the reflection. We don't want to reflect the original. Right? So we're working our way backwards. The last wall we want to bounce off is EF, so that's the first reflection we make. Then, working our way backwards, we want to bounce off the bottom wall, and I reflect the reflection. Okay? Now, what is the ball going to do? So to start our process, we're going to connect the ball to that final reflection. Where it hits the wall, I'm going to connect it to the first reflection. And where it hits the wall, I'm going to connect it to its destination. So my game plan was good. My angles were definitely off with that first original purple drawing. The game plan worked, but if I would have just kind of lined that up in my mind's eye, I wouldn't have ended up making a hole-in-one on that path. I was aiming for the wrong point. But the game plan was good. So we were able to do it once we actually made our reflections. Okay.
Are you good at mini golf?
Okay, so in theory, I should be really good at mini golf and pool. I am horrible at mini golf. Horrible. I am fairly decent at pool. But mini golf, no. Real golf, I've played once in my life. I think I played 2 holes, and I took like 85 swings on those 2 holes, and probably only connected like 12 times, and then I gave up. Like, most of my swings were wild swings at the air because hand-eye coordination is lacking. So I know what should happen. Making it happen is not in my skill set. For your assignments, at the end of the packet is your assignment page. There are 3 problems. So the first one, show the path to get a hole in one. I'm gonna tell you problem 1 you can do with 1 bounce.
Yes.
Problem 2, you're gonna need 2 bounces. Problem 3, design your own mini golf hole or pool table setup, and you must use at least 2 bounces. Some students like really do themselves on this and make like a very, very cool and crazy mini golf hole, and it's as cool as it is. I mean, stretch yourself as far as you want to stretch yourself, but I'm thinking like 2 bounces is good, and sometimes it ends up taking like 10 bounces. That's more work than I'm requiring you to do, but take it as far as you want. Now, where to do that other problem, you can kind of do it in the margin of this page. You can do it on a separate page. My intention was the back of this page would be blank, but something happened, and the back of this page is actually tomorrow's assignment. So that's not going to work so well. So on a separate sheet of paper or kind of in the side margin of those problems, you can do problem number 3.
How's it gonna work for turning?